Hey, we're going to talk about the comparison test, which will sometimes allow us to determine whether or not a series converges by comparing it to a simpler series that we know more about. For example, take a look at the series sum n equals 1 to infinity of 1 over n squared plus 1. Well, it's not a p-series, but it looks a whole lot like the p-series 1 over n squared, which we know converges. And moreover, the terms of the series 1 over n squared plus 1 are smaller than the terms of the series 1 over n squared for all values of n, because a bigger denominator means a smaller number. Now, both of these series are defined as the limits of their sequences of nth partial sums, and the nth partial sums of the series on the right, 1 over n squared, have to each be bigger than the nth partial sums of the series on the left, 1 over n squared plus 1, because the terms are bigger. And since the series on the right, the p-series 1 over n squared, converges to some number, well, how could the series on the left possibly diverge? The terms are all positive. We keep adding them. If it was going to diverge, it would have to be infinite. It would have to be grow without bound. And yet it also has to be smaller. Each partial sum has to be smaller than the corresponding partial sum of 1 over n squared. And this is the first part of the comparison test. Suppose you have two series, sum a sub n and sum b sub n, where the terms of both series are all positive, and sum b sub n is the one that you know something about. Well, then this first part says, if the series sum n equals 1 to infinity of b sub n converges, and the terms of the series a sub n are all less than or equal to the terms of the series b sub n, then the series sum n equals 1 to infinity of a sub n also has to converge. And this is what we have here. We have 1 over n squared plus 1 is less than 1 over n squared for all values of n. And we know that the series sum 1 over n squared converges by the p-test. And so the sum 1 over n squared plus 1 converges by the comparison test. And you notice that I'm not too careful with the n equals 1 to infinity, because it doesn't really matter. If sum n equals 1 to infinity of 1 over n squared plus 1 converges, so does sum n equals 17 to infinity. It doesn't matter what actual number you start at, so we can just consider it the sum of 1 over n squared plus 1. Let's look at another example. Sum n equals 2 to infinity of 1 over n minus 1, and I'm starting with n equals 2, because if I started with n equals 1, I would have a 0 in the denominator for that first term, so I'm trying to avoid that. I know that the harmonic series sum n equals 2 to infinity of 1 over n diverges. Usually we look at the sum n equals 1 to infinity of 1 over n, but since that diverges, so does the sum n equals 2 to infinity. And the terms of the first series, the sum 1 over n minus 1, are all greater than the corresponding terms of the second series, sum 1 over n, because the smaller denominator is the larger number. Meanwhile, we know that the second series, the harmonic series, diverges. It goes to infinity, meaning the limit of the nth partial sums is infinity. And so how could the first series possibly converge when the nth part with each nth partial sum of the first series is larger than the corresponding nth partial sum of the second series, which goes to infinity? And so the first series must also diverge. The limit of the nth partial sums must also be infinite. And that's the second part of the comparison test. If we have a known divergent series, if sum b sub n diverges, and we have another series, sum a sub n, where the terms of the series a sub n are all greater than or equal to the terms of the known divergent series, then the series sum a sub n must also diverge. And so to finish our argument over here, we have the terms of the series 1 over n minus 1 are greater than the terms of the series 1 over n for all n, and we know that the series sum 1 over n diverges. It's the harmonic series. We don't even have to say why it diverges. We've seen it so many times. And that means that the sum 1 over n minus 1 diverges by the comparison test. Let's see if we can get some visual idea of what's going on here. What I'm graphing here are the nth partial sums of b sub n. This is for the first part, where we imagine that the sum b sub n converges to some value L, which means that the nth partial sums, the sequence of nth partial sums, are getting closer and closer to L the farther we go out, the larger n gets. Well, what could the nth partial sums of a sub n look like? Well, all the terms of a sub n are smaller than the terms of b sub n, so each nth partial sum must be smaller. And so it can't possibly go up like this to infinity. That can't happen. And so what has to happen is that it has to converge, maybe not to the same value of L, but it is always smaller than the nth partial sums of the corresponding series sum b sub n, and that's why sum a sub n has to converge. On the other hand, consider what happens in the second case, where the series sum b sub n diverges. Here I'm showing the graphs of the nth partial sums of a divergent series b sub n, and I've tried to make it look like they are going up to infinity. And since the terms of the series a sub n are all larger than the terms of the series b sub n, each of the nth partial sums has to be larger. So I don't know how much larger, but some amount larger. So how could it possibly converge to some value? They would have to stop being larger than the terms for b sub n for that to happen. So that's not what happens. What happens is it has to also go up to infinity. So it also diverges. That second series also diverges. Look what happens instead if you know that you have a divergent series b sub n, and the terms a sub n are not greater than the terms b sub n, but less than the terms b sub n. So then the nth partial sums are smaller. Well, what happens? Well, who knows? One thing that could happen is that they could converge to some limit, and the series would converge. Another thing that could happen is that they could go off to infinity and still be less than the corresponding terms. And so we just don't know in that case. And I probably should have shown the corresponding picture with the series that converges for the first part. If you know that a series converges and the terms of some other series are greater, then what happens? Well, who knows? It could converge to some larger number, or it could diverge. And the key point here is that the comparison test only covers 2 of the 4 possibilities. One possibility is we have some series b sub n that converges, and we have some series a sub n where the terms are less than or equal to the terms of that series. Then we know that the series a sub n converges. But what if we have some series b sub n that converges, and the terms of a sub n are greater than the terms of b sub n? Then what do we know? Absolutely nothing. For the second part, suppose we have a series b sub n that diverges, and the terms of our series a sub n are greater than the terms of the series b sub n. Then we know that a sub n also has to diverge. But what if b sub n diverges, but the terms of the series a sub n are smaller than the terms of the series b sub n? Then what do we know? Absolutely nothing. A sub n might converge or might diverge. And so here it is in a nutshell. To use the comparison test, you have to show that the terms of the series that you're trying to test are either smaller than the terms of a known convergent series, in which case your series that you're testing converges, or else larger than the terms of a known divergent series, in which case the series that you're testing diverges. If you can't show one of those 2 things, you can't use the comparison test. Okay, let's do a couple of examples. Let's look at the series sum n equals 1 to infinity, 1 over n squared plus n. Observe that the terms 1 over n squared plus n are less than the terms 1 over n squared for all values of n. And we know the series sum 1 over n squared converges by the p-test, so that means that the series sum 1 over n squared plus n converges by the comparison test. Just to be clear, all of this is the answer to the question. In other words, if I tell you, test this series for convergence or determine whether or not that series converges, then you have to give all of this argument as your answer. I don't want just yes, it converges or no, it doesn't. Especially don't want no, it doesn't, because it does. But I want this argument to explain why the series converges. Also notice that in this important step right here where we're doing our comparison, I'm comparing the terms of the series, not the series themselves. I'm not trying to say that the sum 1 over n squared plus n is less than the sum 1 over n squared. I'm just saying that 1 over n squared plus n is less than 1 over n squared. All right, let's do another just ever so slightly trickier. Not a lot harder, just slightly harder. And the trick is, how do you decide what series to compare this to? And the answer to that question is, well, you imagine what happens when n gets really large. Like imagine n is 75 trillion. Well, 75 trillion versus 75 trillion minus 1. Basically the same number. 75 trillion cubed versus 75 trillion cubed plus 2. Hardly any difference. The plus 2 really makes very little difference when you're comparing it to 75 trillion cubed. Which is to say that the larger n gets, the less the minus 1 and the plus 2 get, and the more this starts to look like just n over n cubed. And n over n cubed is 1 over n squared. And so that's what we will try to compare to. And the comparison, the showing that the terms of this series are less than the terms of the series 1 over n squared is very important and a key part of the argument. So you don't just want to state it. You don't just want to go straight for n minus 1 over n cubed plus 2 is less than 1 over n squared. How do you know? You want to make it very obvious, so you want to go slowly, step by step. For example, n minus 1 over n cubed plus 2 is very clearly and obviously less than n over n cubed plus 2 because it has a smaller numerator. And similarly, n over n cubed plus 2 is very clearly and obviously less than n over n cubed because n over n cubed plus 2 has a larger denominator, and a larger denominator makes a smaller number. And finally, n over n cubed is precisely equal to 1 over n squared. So this argument shows that the terms of this series are less than the terms of the series 1 over n squared. And then to complete our argument, we have to now say, we know that sum 1 over n squared converges. It's a p-series with p equals 2, so it converges by the p-test. And that tells us that the series that we're interested in converges by the comparison test. And you need all these pieces to complete the answer. Okay, you try this one. Look at the sum n equals 2 to infinity of n over n squared minus 1. And again, I'm starting at n equals 2 to avoid a 0 in the denominator when n is equal to 1. And if you're not sure where to start, imagine that n is a very large number, in which case the minus 1 in the denominator is not really playing an important role in whether or not this series converges, and that should give you an idea of what series to compare it to. All right, pause the video, take a moment, see if you can write up the way that you would write the answer to this on a quiz or an exam, and then we'll go through it together. If you ignore the minus 1, n over n squared is 1 over n, and the sum 1 over n is the harmonic series which we know diverges. So we are going to have to show that the terms of this series are larger than the terms of the harmonic series. And here's how you do it. N over n squared minus 1, certainly larger than n over n squared. because n squared minus 1 is a smaller denominator than n squared, and a smaller denominator makes a bigger number. And n over n squared simplifies to 1 over n. And so we have just shown that the terms of this series are larger than the terms of the harmonic series. And to complete our answer, we have to state that the series sum 1 over n diverges, and then conclude that the series that we're looking at diverges by the comparison test. So it's important to name the test that we're using to explain why it diverges. Let's see how our work would have changed if instead we were looking at the series sum n equals 1 to infinity of 2n over 3n squared minus 1. Well, by very similar logic, we have that the terms 2n over 3n squared minus 1 are greater than the terms 2n over 3n squared, and 2n over 3n squared is 2 over 3n. And the key observation is that the series 2 over 3n is 2/3 times the sum 1 over n. You can pull a constant outside of the series, and so it's 2/3 times the harmonic series, and the harmonic series diverges. And so 2/3 times the harmonic series diverges, which lets us say that the sum 2 over 3n diverges. And since we've already shown that the terms of our series 2n over 3n squared minus 1 are greater than the terms of 2 over 3n, that lets us say that the series that we're looking at diverges by the comparison test. Okay, I want to show you one more example, the sum n equals 1 to infinity of the natural log of n over n. And one way you can do this is by the integral test. You can compute the improper integral, the integral from 1 to infinity of the natural log of x over x dx. It's a substitution problem, it's not that hard. And when you're done, you'll find that that improper integral diverges, which tells us that this series diverges. But I'd rather not work that hard. I'd rather use the comparison test if I could. And in particular, I'd like to say natural log of n over n is larger than 1 over n. The only problem is that it's not strictly true. Natural log of 1 is 0, and 0 over n is certainly not greater than 1 over n. Natural log of 2 is smaller than 1, and so that's not going to be greater than 1 over n either. And the trick is, well, when does the natural log of n become greater than 1 over n? Well, the natural log of e is equal to 1, and e is some number between 2 and 3, and the natural log is an increasing function. And so as long as n is greater than e, and since we're talking about natural numbers, we can start with 3, we have that the natural log of n over n is greater than 1 over n for all values of n greater than or equal to 3. Now, the comparison test said that it had to be for all values of n, but it's not strictly true. It's good enough if it's for all values of n greater than or equal to something or other. In other words, you can throw away the first few terms of the series, and it doesn't change whether or not the series is going to converge. In other words, we can argue that since the sum n equals 3 to infinity of 1 over n diverges, then the sum n equals 3 to infinity of the natural log of n over n also diverges by the comparison test. And since that series diverges, sum n equals 1 to infinity of the natural log of n over n also diverges, and that's by basic properties of series. And the basic property is it doesn't matter if you throw away finitely many terms from a series. Okay, that was the comparison test. It's very useful. There is one very annoying question on the homework. It's only a one-question homework, but as I said, it is very annoying. It's basically got 6 parts or something like that. You have to get them all right. It doesn't tell you which ones you got wrong, and it asks you, can you use the comparison test to show something or other? And look at it very carefully. Don't let it trick you. Read the directions very carefully. Watch out for the possibility that the terms are not all positive. If the terms are not all positive, you can't use the comparison test. So that is one way that they try to trick you in that question. Don't fall for it. All right, have some fun. If you get stuck, let me know. You can email me, of course, anytime. And I'm looking forward to seeing you in class.